A remote volcano rising above the Andean landscape of central Chile has spent thousands of years in relative geological quiet. Generations have come and gone, civilizations have risen and disappeared, glaciers have advanced and retreated, and entire chapters of human history have unfolded, while Nevado de Longaví remained largely dormant. Yet recent seismic activity has placed this long, silent volcanic system back under close observation, after hundreds of earthquakes were detected beneath the mountain in a remarkably short period of time. The development has attracted attention not because an eruption is occurring, but because the volcano's recent behavior represents a significant departure from its long-established pattern of inactivity. Reports of approximately 400 earthquakes clustered beneath the volcanic edifice have highlighted the dynamic processes still operating within Earth's crust, even beneath volcanoes that have shown little outward activity for thousands of years. Nevado de Longaví stands within Chile's extensive volcanic chain, a region shaped by the ongoing collision between tectonic plates along the western margin of South America. The mountain reaches an elevation of roughly 10,500 feet, or about 3,200 meters above sea level. Its snow-covered summit and rugged volcanic slopes form part of a landscape where volcanic activity has repeatedly reshaped the terrain over millions of years. Unlike some of Chile's more frequently active volcanoes, Nevado de Longaví has maintained an unusually quiet profile in recorded history. Geological studies indicate that its last significant eruptive episode occurred approximately 6,000 years ago. Since then, the volcano has remained largely absent from discussions about active volcanic hazards in the region, overshadowed by neighboring volcanic systems that have erupted during historical times. That long period of apparent dormancy is one reason the recent earthquake swarm has drawn interest. Volcanic systems are rarely truly extinct unless specific geological conditions indicate that magma supply has permanently ceased. Many volcanoes can remain inactive for thousands of years before exhibiting renewed signs of unrest. The challenge for scientists and monitoring agencies is determining whether seismic activity represents a temporary adjustment within the crust or a signal of deeper changes occurring beneath the volcano. The recent sequence involved hundreds of small earthquakes concentrated beneath Nevado de Longaví. While individual events were generally modest in magnitude, their collective occurrence within a limited area suggested an active process affecting the volcanic system. Earthquake swarms differ from the typical pattern associated with tectonic faults, where one larger earthquake is followed by smaller aftershocks. Instead, swarms consist of numerous earthquakes of similar size occurring over a period of days, weeks, or months. Such swarms are often associated with volcanic regions because magma movement, fluid circulation, changes in underground pressure, and fracturing of rock can all generate seismic signals. In many cases, the earthquakes are too small to cause damage at the surface, yet they provide valuable clues regarding conditions deep underground. Chile occupies one of the most volcanically active regions on Earth. The country stretches along the boundary where the oceanic Nazca Plate descends beneath the continental South American plate. This process, known as subduction, drives the formation of magma deep within the mantle and crust. Over geological time, rising magma has produced hundreds of volcanoes along the Andes. The same tectonic forces responsible for Chile's volcanic landscape also generate some of the largest earthquakes ever recorded. The interaction between the plates continuously stores and releases energy, creating a complex environment where seismic and volcanic processes often intersect. Nevado de Longaví belongs to a segment of the Andes characterized by numerous volcanic centers, many of which formed during the Quaternary period. The volcano itself is notable for its distinctive geological composition. Researchers have identified evidence suggesting that water-rich magmas played an important role in shaping its eruptive history. Such magmas can influence the style of volcanic activity by affecting viscosity, gas content, and eruption dynamics. Over thousands of years, eruptions from Nevado de Longaví built layers of lava, ash, and volcanic debris that gradually constructed the mountain seen today. Glacial processes later modified portions of the volcano, carving valleys and altering the landscape. The result is a complex volcanic structure preserving evidence of both eruptive and climatic history. The recent earthquake swarm does not necessarily indicate that an eruption is imminent. Around the world, volcanoes frequently experience episodes of seismic unrest without progressing toward eruption. Earthquakes can occur as fluids move through fractures, as rocks adjust to changing stresses, or as hydrothermal systems evolve beneath the surface. Nevertheless, clusters involving hundreds of events often justify increased attention because they represent measurable changes within a volcanic system. Monitoring agencies track such developments carefully, comparing current activity with historical records and looking for additional indicators that might suggest escalating unrest. Among the most important observations are earthquake depth, location, frequency, and type. Volcanic earthquakes are not all alike. Some result from brittle rock breaking under stress, while others are associated with fluid movement. Different seismic signatures can reveal whether activity is concentrated within a shallow hydrothermal system or occurring closer to potential magma reservoirs. At Nevado de Longaví, the concentration of several hundred earthquakes raises questions regarding the source of the activity. Is magma slowly migrating through the crust? Are heated fluids moving through fractures beneath the volcano? Is the swarm related to adjustments in existing fault systems? These are the types of questions that monitoring efforts seek to address through continuous data collection. The significance of a 6,000-year repose period should not be underestimated. Volcanoes with lengthy dormant intervals often present unique challenges because historical records provide little guidance regarding their behavior. Communities and infrastructure may develop around such volcanoes under the assumption that major activity belongs to the distant past. Yet geological records repeatedly demonstrate that long periods of quiet do not guarantee permanent inactivity. Around the world, numerous volcanoes have resumed activity after centuries or even millennia of dormancy. Their awakening serves as a reminder that volcanic systems operate according to timescales far longer than human lifetimes. Understanding those timescales requires looking beyond historical observations. Geological investigations reveal evidence of ancient eruptions preserved in volcanic deposits, ash layers, and lava flows. These records provide insight into eruption frequency, magnitude, and style. For Nevado de Longaví, such evidence indicates that the volcano was capable of significant eruptive activity during its active phases. Ancient eruptions likely transformed the surrounding landscape through the emplacement of volcanic material across broad areas. Ash clouds may have dispersed fine particles over considerable distances, while lava flows reshaped local topography. The deposits left behind now serve as geological archives documenting the volcano's past behavior. Modern monitoring technology offers capabilities unavailable during previous centuries. Networks of seismometers can detect even minor earthquakes occurring deep beneath volcanic systems. Satellite observations measure subtle changes in ground deformation, sometimes detecting uplift or subsidence of only a few centimeters or inches. Gas monitoring instruments identify variations in volcanic emissions that may indicate changes in underground conditions. When multiple monitoring methods are combined, scientists gain a clearer picture of volcanic activity. Earthquakes alone provide important information, but their interpretation becomes more robust when considered alongside deformation measurements, thermal observations, and gas data. One of the key questions surrounding any earthquake swarm is whether seismic activity remains stable, decreases, or intensifies over time. A declining number of earthquakes may indicate that the triggering process is diminishing. Persistent activity could suggest continued underground adjustments. Increasing seismicity, especially when accompanied by other changes, may warrant heightened concern. Volcanoes are complex systems where pressure, temperature, fluid movement, and rock strength interact continuously. Small changes in one component can produce detectable effects elsewhere within the system. Earthquakes often represent the most immediate evidence of those changes, because fractured rock generates seismic waves that travel through the earth and can be recorded by monitoring instruments. The Andes provide countless examples of volcanic diversity. Some volcanoes erupt frequently, producing relatively small events separated by years or decades. Others remain dormant for centuries before reactivating. The interval between eruptions can vary enormously depending on magma supply, crustal conditions, and regional tectonic influences. Nevado de Longaví's 6,000-year quiet period places it among volcanoes characterized by long-term dormancy. Such systems can accumulate geological changes over extended intervals, making renewed unrest particularly noteworthy from a monitoring perspective. The broader geological setting surrounding the volcano contributes additional complexity. The Andes are not a static environment. Tectonic forces continuously deform the crust, generate faults, and influence magma pathways. These processes can alter conditions beneath volcanic systems over thousands of years. Earthquake swarms sometimes occur when pressurized fluids exploit existing fractures within the crust. As fluids move, they can increase pressure within rock formations, triggering numerous small earthquakes. Similar processes have been observed at volcanoes worldwide, often without leading directly to eruption. In other cases, swarms accompany magma intrusion. Rising magma exerts pressure on surrounding rocks, causing fracturing and generating seismic activity. Distinguishing between these scenarios requires detailed analysis of seismic patterns and supporting observations. The presence of glaciers and snowfields on Nevado de Longaví introduces additional factors into the volcanic environment. Water derived from melting ice can interact with volcanic systems, influencing hydrothermal circulation and potentially affecting subsurface conditions. Over geological timescales, the relationship between volcanic heat and surface water contributes to the evolution of the volcanic edifice. Climate also plays a role in shaping the volcano's appearance and geological record. Repeated cycles of glaciation and deglaciation have modified volcanic landscapes throughout the Andes. Valleys carved by ice, deposits left by glaciers, and altered drainage systems all contribute to the modern terrain. Despite the attention generated by 400 earthquakes, it is important to place the activity within a broader context. Earthquake swarms alone do not provide definitive evidence that an eruption will occur. Many volcanic systems experience unrest episodes that eventually subside without producing surface activity. Historical examples from around the world demonstrate the wide range of possible outcomes. Some swarms conclude after weeks or months, leaving little lasting impact beyond improved scientific understanding of the volcanic system. Others precede eruptions by months, years, or even longer periods. The relationship between unrest and eruption is rarely straightforward. The significance of the recent earthquake swarm becomes even clearer when Nevado de Longaví is viewed within the broader geological framework of central Chile, one of the most tectonically active regions on the planet. The volcano exists because of processes that have been operating continuously for tens of millions of years, gradually constructing the Andes while simultaneously generating powerful earthquakes, volcanic eruptions, mountain uplift, and crustal deformation. Off the western coast of South America, the oceanic Nazca Plate moves steadily eastward and descends beneath the continental South American plate. This collision zone, known as the Peru-Chile Trench, stretches for thousands of miles and kilometers along the Pacific margin. Although the plates move only a few inches or several centimeters per year, the cumulative effect over millions of years has transformed the continent's western edge into a vast mountain chain. As the denser oceanic plate sinks into Earth's mantle, temperatures and pressures increase dramatically. Water trapped within minerals of the descending slab is gradually released into the overlying mantle. This addition of water lowers the melting point of surrounding rocks, generating magma that slowly rises through the crust. The process is responsible for the extensive volcanic arc that extends through much of the Andes. Nevado de Longaví occupies a particularly interesting position within what geologists call the southern volcanic zone of the Andes. This volcanic belt contains dozens of active and dormant volcanoes distributed across central and southern Chile and neighboring Argentina. The region is characterized by a remarkable diversity of volcanic styles, magma compositions, and eruptive histories. One feature that makes Nevado de Longaví unusual is its magma chemistry. Geological studies of volcanic rocks collected from the mountain reveal compositions that differ somewhat from those found at many nearby volcanoes. The volcano is known for producing magmas unusually rich in water compared with typical arc volcanoes. This characteristic has attracted considerable scientific interest because water plays a crucial role in determining how magma behaves underground and during eruptions. Water-rich magma tends to be less dense and may rise more efficiently through the crust. At the same time, dissolved gases carried by the magma can influence eruptive behavior if pressure decreases near the surface. The interaction between magma, gases, and surrounding rocks creates a complex system capable of generating diverse volcanic products. The crust beneath central Chile is itself far from simple. Rather than forming a uniform block of rock, it consists of numerous fault systems, ancient intrusive bodies, sedimentary basins, and remnants of earlier volcanic episodes. Magma ascending from depth must navigate this intricate geological architecture. Some magma reaches the surface and erupts. Other magma cools and solidifies underground, forming plutonic bodies that may remain buried for millions of years. The recent earthquake swarm beneath Nevado de Longaví may reflect movement along fractures within this complicated crustal environment. Rocks subjected to increasing stress eventually crack, releasing seismic energy. If fluids or magma are involved, the process can generate hundreds of small earthquakes as pressure migrates through interconnected fracture networks. Understanding the volcano also requires examining its relationship with neighboring volcanic centers. The Andes do not consist of isolated volcanoes operating independently. Instead, they form part of a regional magmatic system influenced by common tectonic forces. Changes affecting one portion of the crust can sometimes alter stress conditions elsewhere. Throughout central Chile, evidence of past volcanism is visible across the landscape. Ancient lava flows, volcanic domes, pyroclastic deposits, and deeply eroded volcanic remnants record millions of years of activity. Many mountains that appear non-volcanic today are actually the worn remains of volcanoes that erupted long before modern humans appeared. The region surrounding Nevado de Longaví contains rocks spanning a wide range of geological ages. Some formations originated in ancient marine environments when portions of the area lay beneath the ocean. Others formed through volcanic eruptions or intrusive magmatic activity associated with Andean mountain building. This layered geological history provides a record of changing environments stretching back tens of millions of years. Mountain uplift remains an ongoing process. The Andes continue rising as tectonic forces compress and thicken the crust. Although uplift rates are generally measured in millimeters per year, the cumulative effect over geological time is enormous. Peaks exceeding 10,000 feet or 3,000 meters owe their existence to these long-term tectonic processes. Erosion works simultaneously to wear the mountains down. Rivers carve valleys, glaciers sculpt ridges, landslides reshape slopes, and weathering gradually breaks rock into sediment. The modern landscape represents a balance between uplift and erosion, with both processes operating continuously. Glaciation has played an especially important role at Nevado de Longaví. During colder climatic periods, glaciers extended farther down the volcano's slopes than they do today. Moving ice acted like sandpaper, grinding rock and carving characteristic U-shaped valleys. Glacial deposits preserved around the volcano provide clues regarding past climate conditions and landscape evolution. The interaction between glaciers and volcanism can produce distinctive geological features. Ice can influence drainage patterns, alter erosion rates, and affect the stability of volcanic slopes. In some volcanic regions, eruptions beneath ice have generated unique deposits formed by rapid melting and explosive steam production. While Nevado de Longaví's most recent known eruptions predate modern observations, evidence preserved in surrounding rocks helps reconstruct these ancient interactions. Hydrothermal systems represent another important component of volcanic geology. Even when a volcano is not erupting, heat from deeper magmatic sources may continue circulating groundwater through fractures and porous rock layers. As water moves through hot rocks, chemical reactions alter minerals and create zones of weakened material within the volcanic edifice. These hydrothermal systems can remain active for thousands of years after major eruptions cease. They also provide one possible explanation for earthquake swarms. Pressurized fluids moving through fractures may generate seismic activity without requiring significant magma movement. Distinguishing between fluid-driven and magma-driven earthquakes is therefore a central objective during periods of volcanic unrest. The broader tectonic setting introduces additional complexity. Chile experiences some of the world's largest subduction earthquakes because enormous sections of the plate boundary periodically rupture. These major earthquakes can alter stress fields across vast regions. Researchers continue studying how large tectonic earthquakes may influence volcanic systems, either by changing crustal stresses or modifying fluid pathways underground. The geological record suggests that the relationship between tectonics and volcanism is deeply interconnected. The same subduction process responsible for generating magma also produces powerful earthquakes and drives mountain building. Nevado de Longaví exists because of this ongoing interaction. Ancient eruptive deposits found around the volcano reveal that its activity was not limited to a single event 6,000 years ago. Rather, the mountain experienced multiple eruptive phases over much longer timescales. Layers of ash, lava, and fragmented volcanic material document a history of repeated construction and modification. Each eruption contributed new material to the growing volcanic edifice. Lava flows added thickness to the mountain's slopes. Explosive eruptions dispersed ash across surrounding areas. Subsequent erosion reshaped these deposits, creating the landscape visible today. The volcano therefore represents not a single geological event, but the accumulated result of countless processes operating over hundreds of thousands of years. The recent sequence of approximately 400 earthquakes serves as a reminder that the geological engine responsible for creating the Andes remains active. Deep beneath Nevado de Longaví, tectonic forces continue shaping the crust, just as they have for millions of years. Whether the current unrest proves temporary or marks the beginning of a longer period of activity remains uncertain. What is clear is that the volcano occupies one of Earth's most dynamic geological environments, where plate collision, mountain building, magmatism, glaciation, and erosion continue to interact in ways that constantly reshape the landscape of central Chile.